So good morning or good afternoon, everyone, depending on where you are. Today, we are super happy to welcome Professor Jon Aurnou from the Department of Earth, Planetary and Space Sciences at the University of California. And he will talk to us about atmospheric river, and he will do some presentation with lab experiment, and I cannot tell you how happy I am to see some lab experiment. So Jon, the floor is yours.
Okay. Thanks everybody. Thanks for showing up late in the afternoon. First things first, for everybody who can, turn on your cameras. I like seeing people who I'm talking to, so if you do have a camera, feel free to turn it on so I can see you. I actually went to a workshop where they showed the more cameras on, the more people take in. Good to go. For questions, ask questions during the talk. You do not have to wait. You can just chime in and ask away. Is everybody with me? Anyone? Anyone? I'll take that as a yes. Okay, so what we're going to do is we're going to do a couple of desktop experiments, and then we're going to try to go over the physics of what happens really in the wintertime atmosphere and what sets the large-scale fluid response in a wintertime atmosphere on Earth. And in so doing, we'll learn it's the wrong place, but we'll learn kind of mid-latitude weather in the wintertime in the northern or southern hemisphere. A little bit far from the equatorial region for Kigali, but it's okay. It's still really cool physics. So let's do it. So first things first, I'm going to just show you my setup. We're here, we're in my lab, and I've got two desktop experiments. One that you can see that's rotating because Earth rotates, and I need rotational physics to get the physics right. And another that's non-rotating. So this is we'll call it an incredibly slowly rotating planet. And on each of these devices, I've got a beaker in the center of the tank of water. And that beaker, in this case, is filled with ice and a couple of heavy sinkers at the bottom to keep the beaker in place. So the pole right at the center of the tank, I'm calling that the North or South Pole. The North or South Pole is cold, and cold water is dense. So we'll see what happens when I put a little dye in this non-rotating tank. So look in, there it is, at the non-rotating tank. I'm going to put in some blue food coloring right here. There's a little there. I'll put a little there. I'll put a little there. And I'll put maybe 4 drops in. Okay, so what you can probably see is the dye sunk. And I'm going to look from above. And I can't really see what you see. It's sinking down. Oh, and I can't hit the arm on the other tank, or that ruins the other experiment. It's sinking down, and then it is slowly spreading outwards in cylindrical radius. Why? Because the dye is slightly dense, and the water next to the ice beaker is very cold, and it's dense too. So it sinks down, and then it can't move inwards because the beaker's there, so it has to spread outwards. Does that make sense? And so if we wait a while, we'll see that will simply continue to radially spread outwards from the beaker. Okay, that's the first experiment. And I'm trying to get a good view. It's really hard to see on the bottom. I don't know if you can, but it's simply plating outwards and it's moving downwards. Everybody with me? And in addition, if I waited long enough, if I put some, I'm going to do one more thing. We're having fun here. If I put some red dye out here, boom, 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 boom. Here's the red dye I've just put in farther out. If I put some red dye further out, it will sink down. And we could imagine that as warmer air farther from this cold North Pole. Well, in time, the blue dye would push the red out of the way. And you could even imagine it would form a big circulation cell where eventually enough cold blue would spread out that it would push the red up and back towards the axis. It would form what's called a circulation cell. Okay. Now, let's try doing the same thing on our rotating tank. And the first thing I have to do, I'm going to set this up here. Here's the rotating tank. First thing I have to do is add some ice. And so I have a thing of ice here. Gonna try not to spill it into the water. Oh, that's it. I keep forgetting about that arm. Excuse me. That's the one thing I can't do is stop the rotation. Planets don't do that much. So there's that. There's some ice. There's some more ice. Okay, so now I've got ice in there. So now it's forming a cold pole. And now I'm going to add some water to the beaker, which thermally couples the ice to the wall of the beaker. Okay. So now I'm going to put in the same dye, and we're going to see what happens in the rotating frame. Again, in the non-rotating frame, things simply spread out radially. The blue just spreads out in cylindrical radius. Now, let's pin to the rotating frame, and let's do the same experiment. I'm going to do 1, 2, 3, 4. So I put 4 dye drops near the tank, and I'll put roughly 1, 2, 3, 4 dye drops out here. So I've got cold, quote unquote, blue water near this polar beaker. And I've got quote unquote warm equatorial water out by this outer radius. You can think of that as the equator and this as the North or South Pole. The system's right-handed in its rotation. So you could imagine that it's somewhat like the North Pole. And one thing you see first, if I switch cameras, I'm going to unpin for a sec. How do I unpin? I'm going to remove the pin. And if I look on this camera, you can see there's a big, you can't. There's a big swirling flow that's wrapping around this way. And so if you look, there's a huge swirl. It's swirling and swirling and swirling like crazy. It's like a polar jet stream. And if you look from above, that's now starting to break apart and wrap around into big storms. Do you see those big storms? There's a big one, excuse me, right here. Ooh, and it's mixing, making an eddy here. And there's another polar storm forming right there. And so we're just going to wait 1 minute and let it form a little more. Oh, there's a really nice plume. Ooh, right here. There's another, what's called an instability right there. So the fluid's wrapping around like this, and then at some point it explodes away. But it doesn't explode radially. It gets wrapped up into a big circular storm. And so, oh, there's another big one right there. So big instability there, big instability there, big instability there. And what I'm going to do, I'm going to put some dye right in front of this big storm right here. And we're going to see if it gets caught in it. And if it does, we will see it gets wrapped around it. Come on. Come on, experiment. Do your thing. My problem is I can't see it. The camera sees it pretty well, but good. So if you look, I need like a pointer. If you look, pointer thing. Give me one sec. All right. So if you look right about, right here. If you look right here, there's a line of red. You see right here, there's this line of red. It's wrapping around this big storm, this big, what's called an eddy. It's wrapping around this big eddy. And the red is being carried from quote unquote the equator all the way to the North Pole in a very thin sheet of red fluid that wraps right around the edge of the storm. That is technically an atmospheric river. That is actually how most big water vapor transport phenomenon occur across the mid-latitudes in the atmosphere. So when you see this thin filament of red, you can imagine, oh, it's coming from the equator, it's warm and moist air, and suddenly it's getting ripped all the way towards the pole by this along the edge of this massive storm. That is what happens in the atmosphere. That's what controls water vapor transport between basically low latitudes and high latitudes on Earth. Okay, everybody good? Did everybody see that roughly?
Yes.
Awesome. We'll take it. So is this rotating system rather different from the non-rotating system? My answer is fundamentally. This, I hope, looks a little like big storms you see in maps of the atmosphere. While if you look at my non-rotating tank, I'm going to remove the pin. Boom. Here's my non-rotating tank. Yeah. Still just spreading out radially. I hate to say it's boring, but it's relative to the other one. I mean, that's like doing the most weird, awesome stuff. That is fairly simple. It's moving away from the cold source. Sensible, but maybe not so surprising. When you add rotation, you get all these vortices and you get all this complexity. And that complexity is really joyous physics, really hard and very fun. So that's my experiment. I'm now going to try to share. I'm going to pin on me. There's me. And now I'm going to share my screen. Share. And now I'm going to do my talk. Great. Oh, and how do I'm going to hide the meeting controls. Give me one sec. Great. Okay. Can you guys see my slides?
Yes.
Good. You can still see the experiment hidden there on the right side, I hope, but you can also see my slides. And we're going to talk about basic dynamics in the atmosphere and try to understand the experiment we just saw. I was going to do a lab tour. Yeah, I'll quickly do a lab tour. What I do, just so you guys know, I study the fluid turbulence that exists inside planetary cores, deep atmospheres of gas planets, and in the subsurface oceans of, say, the icy moons like Europa and Enceladus, which have oceans underneath their icy surfaces. And so in all those cases, it's rotation mixing with fluid turbulence. And the amazing thing that happens is that out of small scale turbulence on large scales in planets, you organize very coherent large scale structures. Like in the liquid metal core of the Earth, you generate Earth's large scale dipole magnetic field. It's incredible. That comes out of small scale turbulence in the liquid metal core. Amazing that that comes out of turbulence. On Jupiter, you get big jets. So we build big devices that rotate, like these shown here in my other lab. And we heat them from below, we cool them from above, they start to convect, and then we try to measure and characterize the behaviors of the turbulence in rapidly rotating systems on the left in water and on the right in liquid gallium. And so we compare supercomputing models like this big one of a planet there by my colleague Thomas Gastine in Paris to the lab experiments we carry out shown by these kind of inset images. And they compare rather well. And so then we can learn stuff by comparing supercomputing simulations to lab experiments. Lately, I'm working on how we could make a dynamo at the base of the mantle in the early Earth, a so-called basal magma ocean dynamo. I'm working again with supercomputer modelers, not Schaefer and Grenoble. And we're also in our lab, actually right behind me is this device. We're trying to make jets like you have on Jupiter in a very strange device that we've built here, which isn't actually a sphere, but it's like a part of a sphere. And when we measure the free surface temperature field, we see these jet flows. We see these really crazy motions in the temperature field. And those are jets, just like on Jupiter. So we can make Jupiter in the lab. And I don't care about that. And the other thing I do is I like to play with desktop versions of these big devices. These big devices are nothing anybody else can use if they don't visit my lab, and that stinks. So I've been building kind of toy models like the one you're looking at, and they are much more accessible. You can build these with a record player, with any motor. and we can study the kind of physics we have in planets. Okay, so that's what I do in my day job. Let's now talk about what we have for wintertime weather in either hemisphere away from the equator. And so what you have is you have what's called the polar vortex. And the polar vortex is this big blob of cold air that forms over the pole in each winter. It's cold and dense. And every now and then it will become unstable. And when it does, this cold air comes down to the mid-latitudes. And you always see pictures in the newspaper here in the US with just miserably cold people. And they say, oh, the polar vortex has invaded Chicago. Yeah, and it has. That is what you're looking at. And so in the center of the continent, it just gets cold. It gets down to, you can see here, it gets down to as cold as minus 30 degrees C. Really cold. And interestingly, on the same days that it's incredibly cold in Chicago, it tends to be very warm in Alaska. And so that's because you're moving cold air down. It's hitting Chicago. Something else has to replace it because you can't have a vacuum. So warmer air comes up from the mid-latitudes. And next door in Alaska, it tends to be warm on those days. And we in a sense, we'll try to explain that with our model here. Oh, yeah. Oh, so wait, I'm going to go back. Ooh, wow. So there are great flows in here. No, I'm going to hold off. I'll hold off. But if you look in that little one, you can see we have some big storms with some big rivers. There are two big red structures going from near the equator towards our icy poles. So we have that occurring in our tank. And so here's that polar vortex, big lens of cold polar air. It's dense. It tries to spread out. Well, that's just what happens in this tank. In the non-rotating tank, it just spreads out, right? It just spreads radially. So it tries to sink and spread, but in a rotating system, instead it gets wrapped around because Coriolis wraps everything around. So it wraps things around and eventually it goes unstable. But first, right, so it wraps things around. You get this big swirling flow. We actually had that in our tank for a moment. And then it becomes unstable. You could say, oh, it gets wrapped around by Coriolis. That doesn't mean it's dynamically stable. It's not happy that way. At some point, it says you're wrapping, and then it explodes and can't be in that state anymore. And when it becomes unstable, that's when it comes down and visits Chicago. That's when stuff at the North Pole comes down to the mid-latitudes, when the polar vortex rips itself apart. So then it's cold in Chicago. And in addition, that's when we get atmospheric rivers where I live in Los Angeles, or in Santa Barbara, or San Francisco, or Vancouver, anywhere along the west coast of the US and Canada. I don't know. I think in winter, they don't make it to Mexico. They're usually higher latitude. And so where there are these big dips in what's called the polar jet stream, the flow that wraps around the polar vortex, when that comes down to the mid-latitudes, that's when it's super cold. We also get blizzards then, big snowstorms. And it's crazy. Now, why does that lead to atmospheric rivers? Okay, so here's an image of the total water vapor that's contained in a column of the atmosphere. So we've taken a satellite image, we've essentially integrated through the entire atmosphere and flattened the atmosphere and measured how much water vapor is there. And the amount is usually a number of centimeters, roughly 5 centimeters, where it's really moist. And what you see, this is an image during one of these big wintertime instabilities of the polar vortex. You see, there's my cartoon crenellation of the flow that wraps around the polar vortex, where it comes down over the US right here. Oh, that's where it's cold and there are blizzards. Yeah, but look over the Central Pacific, and you'll see the edge of that big crenellation is a very thin, long filament of high water vapor content air. That's an atmospheric river. Really long filament of moist stuff. Let me see. I'm going to turn on a real-time image from this page. Yeah, this is today's weather. And what you can see is there aren't many huge crenellations right now, but there are a couple. Here's an atmospheric river. In the southern hemisphere, there's a nice atmospheric river. Here's a nice one forming. Anywhere you have a long, thin tendril of high water vapor content air, that's an atmospheric river. Okay, so where did my talk go? Where did my talk go? So, okay, so there's an AR in the middle of the Pacific. And here's another image from NASA Giovanni data. And you can see this green filament is a huge atmospheric river. And this formed January 3rd, 2023. That's the data. And this long filament starts near Hawaii and comes all the way over to the eastern edge of the Pacific Basin and runs into the western edge of the continental United States. And when it does, it hits the topography of the continent. That raises up the air. When you raise up air, it cools, and it then can't hold the moisture, and it rains like crazy. That's called orographic precipitation. So you get this thin, low-level jet, super moist. It runs across the Pacific, and it smacks into the west coast of the US. And that's what controls all our climate. I know, sorry, I'm talking about my climate, but it's what I've had fun playing with because I get them in my tanks. Okay, and this dominates the precipitation budget on the west coast of most continents. Typically, these atmospheric rivers carry about 90% of the moisture across the mid-latitudes. They just do all the big damage in terms of bringing moisture to these regions. So let's take a look at it again. Here's this data, and here's another satellite image. The brown is cold. It's actually showing, again, water vapor. It's very dry air. It's coming from the pole. The air at the pole is cold. Cold air can't hold much moisture. So it looks dry because it is. Polar air is dry. It comes down into the middle of the Pacific. You could see it kind of runs into Hawaii, and from Hawaii to the edge of the continent, there's this thin, heavy, moist, super high moisture content filamentary structure. And I'm arguing we get those in our tank as well. These storms we see in our tank are often rimmed by that red was moist air from the equator, so to speak. So we get the same thing in our tank. The physics is actually the same. So if we can explain the tank, we can understand what's happening in Earth's atmosphere as well. Okay, so here's our tank. There's the front of one of these instabilities of the polar vortex. The atmospheric river's really rimming that. And it's carrying moist, warm air from Hawaii and dropping it off, maybe in Los Angeles or Santa Cruz, anywhere, Vancouver, somewhere along the west coast of the continent. Does that make sense?
Yes.
All right, hopefully. All right, so that's the idea. Now let's do the essential fluid dynamics. I'm going to have to hide this so I can see my own slide. So let's talk about Newton's second law. It's F equals ma, yes? But when we're doing, actually, I need this somewhere else. I need to be able to see, where can I put the, there we go. So it would be F equals ma, or the way I've written it, if you look, it's really ma equals the sum of the vector forces, right? The summation is sigma, and F is all the forces acting. In a fluid, I don't really have a mass. There's not a point mass. So I break up the system onto a fixed grid. It's called an Eulerian grid. And I define the density of the fluid everywhere on that grid as rho. Rho is the density. It's the mass per unit volume. And when I break up the grid into this grid, each little grid cell has a volume dV, little delta V, delta volume. So then the mass is rho times dV. That gives you a feel for the mass. And so rho dV is the mass, and U in fluid dynamics is the velocity. Why it's not V, I don't know. Maybe because V is already volume. And so this is rho dV is mass, and du dt is the acceleration of the fluid. So that's ma equals the sum of forces. Good? And then since the grid is fixed, we can divide out by dV. dV is just some constant that we've defined on our grid. So then rho du dt is the summation of forces per unit volume. Okay, that's still just Newton's law. And we call it Navier-Stokes when we're in a fluid or a continuum. And so what are those forces in a fluid? Well, you have pressure gradients. If the pressure is higher on one side of some air parcel and lower on the other, the air tends to move down gradient. It moves towards low pressure. Why? It's getting pushed hard on one side and not pushed very hard from the other. So it flows down gradient. Okay, if gravity is acting on it, it pulls down. Yes. And if there's viscosity, that tends to slow down the velocity field. That damps the energy. Okay. Now, we live on a rotating planet, so we'll often transform into a rotating frame to get all the physics right. And so when we transform the Navier-Stokes equation into a rotating frame, pressure actually doesn't change its form, gravity doesn't change its form, viscosity doesn't change its form, but the acceleration term changes. Du dt, when we measure it in the rotating frame, has two extra terms. It has Coriolis, this 2 omega z hat cross u, and it has centrifugation, omega squared s. Okay, what's omega? Omega is the rotation of the whole planet. It is the angular velocity. Z hat is vertically upward along the rotation axis. U is the velocity. S is cylindrical radius. That's what we get. So I'm going to simplify this. One, I'm going to move centrifugation onto the right side of the equation, and I'm going to tuck it in with gravity. And I'm going to make an effective gravity that includes both the pushing out from centrifugation and the downward pull of gravity. Fabulous. So now I just have a new gravity, and I can, in a way, stop thinking about centrifugation at first order. And so now I'm going to skip the entire right side. I'm going to say no pressure gradients. Let's not worry about gravity, and let's not worry about friction. If I just worry about the inertia term, as it's called, du dt, and Coriolis, then what kind of solutions do I get? Oh, I have the most gorgeous storms here. Sorry. I should stick with this. If I just have those two terms, I get circles. Why? Well, because let's say I have some initial velocity. Let's say the velocity is initially in this direction. The Coriolis term pushes to the right of that. It's z cross u. Z cross u. Okay, it pushes. In this case, that would appear to be left-handed. But if I move that term onto the right-hand side, you'd see it push off to the right of wherever the velocity is going. So it always pushes off perpendicular to wherever the velocity wants to go. And that tweaks it a little bit. Wherever it's going, it's always pushed off to the side. And if something's always just pushed off to the side, one, it does no work. So you don't change the amplitude of the velocity, but you're continually changing the direction. And so it eventually wraps into a circle. And if you do the math, you see that the radius is related to the speed of the object and the rotation rate of the system. Okay, you shouldn't believe me. So I built a system to do this. And I cut out gravity by making a paraboloid. If you add lab gravity to centrifugation, you get a parabola. So I bought a little parabola. It's over in the corner. I think you can see it. That's right there, that little parabolic dish. I put it on a record player, and we rolled some balls in the rotating frame. And you might say, I don't see any circles. Do you see any? I don't see any. Why don't I see any? I just told you there's circles. I don't see any because we're not in the rotating frame. We're viewing right here from the lab frame. We're looking at a rotating system, but we're not in it. So you can also see up here, I put my camera in the rotating frame. So let's watch the same movie in the rotating frame. That's the exact same. Oops, sorry. That's the exact same experiment. And now you see all the paths of these rolling ball bearings are circles. And one of them, the dark one, is plastic and frictionally damps out. Oh, and when it runs into the other ball, it goes back to being circles. Every path is a circle in a rotating frame. So in a rotating frame, a free particle in motion always lives in circular motion. So it's a real change to Newton's laws. Okay, so that's our system. Now we can expect to see circular structures then in all the rotating fluid physics in atmospheres and oceans. And if we are doing, I'm going to simplify this to save time. If we're doing a thin atmosphere, then in the vertical direction, we're going to claim there's not much velocity. You might say, no, there are big storms. On average, the velocities in the vertical direction are weak in the atmosphere. So we'll claim it's static. And in that case, the only forces acting in the vertical, there's no motion, is the pressure gradient and gravity. And if you balance those two, then you get what's called a hydrostatic balance. And that means the pressure drops off with elevation. It's some P naught, where P naught's the pressure on the surface of the planet. And then it gets less and less as you go up in Z, as you go up in elevation, because you have less material basically on your head, right? As you go higher and higher, there's less stuff above you. So the pressure of overlying material on your head is less. It's the same as if you jump in a river. The deeper you swim, the more your ears hurt. Why? Hydrostatic balance. There's more mass above you, increasing the pressure. So that's the vertical balance. And amazingly, weirdly, in the horizontal direction, on large atmospheric scales, like on the size of an ocean basin, the only two terms that matter are Coriolis and the pressure gradient. It's so weird. So there's no inertia. Du dt is small. The acceleration's small, very small. Friction's tiny on the scale of an entire ocean basin, thousands of kilometers in horizontal width. And gravity doesn't act in the vertical direction. So all we're left with horizontally is Coriolis and pressure. Okay, and that holds above about 100 kilometers in atmospheres and on scales larger than about 10 kilometers in the ocean. So for all the large scale motions, this is called geostrophy or geostrophic balance, and it wins. So let's try to understand what this says. To get to it, I like to take z hat of this whole equation, z hat curl of that geostrophic balance. And what do you get? What is z hat cross a bunch of constants? Rho, we'll call rho the mean density. It's a constant. Omega, the planet doesn't change its rotation rate. It's a constant. So it's z hat cross the velocity. Oh my God, what the hell is that? So let's think about it. Let's say that the velocity is in x. I'll call x whatever this way is. So if I start off in x, but now I want to do z hat cross x, that's actually in y. Okay, so now I'm in y. Z hat cross y, that's minus x. So z hat cross z hat gives me minus of my original direction. So then I can rewrite this. And I can write u, putting the minus sign on the other side, is 1 over 2 rho omega, a bunch of constants. And then you get minus grad p, again, the pressure force cross z. So that's what happens if you play with all your minus signs. Okay, so now what's this mean? It means wherever the pressure force is, pressure force, let's say, is again in x, then it's x cross z. It's to the right. In the northern hemisphere, the flow is always to the right of the pressure force. That is so weird. It's so weird. But that's what happens in large scales in the atmosphere. So the geostrophic flow in the northern hemisphere, in the southern hemisphere, it's to the left. It's just a minus sign because you're upside down with respect to z hat. But it's just a minus sign. But in the northern hemisphere, the geostrophic flow is always to the right of the horizontal pressure force. And what's even weirder is that means the flow is always along constant pressure lines, isobars. Why? Because the flow is never down gradient, so it always has to be along a constant pressure line. That's incredible. That's why you always see pressure maps when they're doing meteorology, because the flow is along the pressure lines. Okay. So let's do an example. Let's say there's some line of high pressure, and then going into the page somewhere in the back is low pressure. Normally in a non-rotating system, the flow would go from high to low, go right into the page. But if the system's rotating, then it has to go sideways. And so the flow would actually be exactly between the two, off to the side. It's so weird, but that is the physics. That's the rotational physics. Okay, now let's do it again. Let's do another example where we're going vertically. Let's say there's high pressure at some elevation, we'll call it Z1, at the base of the atmosphere. If you see just a high pressure, it means it's high pressure on that horizontal surface, Z1. It means outside of it, it's surrounding it is lower relative pressure. And so the fluid, like in our experiment here, would try to spread out from that high pressure system. But when it spreads out in a rotating frame, it gets wrapped around to its right. The pressure is radially outward, so the flow is always to the right of that pressure force. So instead of going out in S, it'll go around in phi. And in this case, it'll go retrograde. It'll go slower than the planet. Why? Because it's trying to move out, and to the right is always in negative phi hat. If above this, at some higher elevation, let's say there's a low. Well, now fluid would try to come in radially to that low, but geostrophically, it always get pushed off to its right. So everywhere it would go to the right, and it would wrap around in this opposite direction, and it would be prograde. It would be flowing faster than the planet. And actually, those are two stable solutions. Those are the solutions you'd get. So that's geostrophic balance. It's very strange. And yet that's how atmospheric large-scale flows work. So now let's get a little closer to understanding how the planet works, which is that the planet doesn't have constant density everywhere. It has big lateral gradients in density because it's much warmer at the equator than it is at the poles. So the density at the poles is lower. The density at the equator is lower than the poles, right? Where the temperature is low at the poles, the density is high. Okay, so let's try to figure that out. Here's an incredibly good drawing I made on my iPad. And this shows the surface of the Earth. Y is pointing towards the pole. So the equator's on the right-hand side, pole is on the left. And we're going to assume there's constant density equatorial air for half of the planet. And there's polar blue high density air on the polar half of the planet. And let's figure out what happens with the pressure field. First of all, you'll see, the tropopause, that's basically the height of the atmospheric layer we live in, where all the mass is, basically. And in this constant density universe, very simplified, the tropopause has to be higher. The edge of the atmosphere in this oversimplified world is higher at the equator than it is in the pole. Why? Because the pressure is roughly constant at the surface of the Earth. And so if the density is higher at the pole, then the atmosphere has to be thinner to have the same mass of material above you as at the equator. Okay, so it's a little thicker at the equator. And we know we have hydrostatic balance in both sections. So in either way, we start off at P0, the surface pressure, which is 1,000 millibars, which is about 10 to the 5 pascals. And then it falls off. It gets less and less as we go up through the atmosphere. There's less and less material above your head. Your ears hurt less and less as you go up through the pool, right? So let's draw that. So in this plot, elevation is on the y-axis and pressure is on the x-axis. And I'm starting at 1,000 because that's surface pressure, about 1,000 millibars. And so the base location is Z0 of 0, surface of the Earth, P0 of 1,000 millibars. And if I plot that in the equatorial region, okay, then as I go all the way to quote unquote 0, all the way through the tropopause, up to the tropopause, then the pressure falls off this way. And it hits the tropopause at about 11.5 kilometers in this model, very simplified. But in the polar region, it falls off faster because the density is higher. So if I plot the polar pressure, it literally is decreasing faster because rho p, the polar air, is cold and dense, denser than the equator. So now if I compare what's the pressure difference, there's no pressure difference at the surface. But at elevation, there's a big pressure difference. It's higher pressure at 8 kilometers high. The pressure is, man, it's more than 100 millibars higher at the equator than it is at the pole. And that decreases as you go towards the surface, right? So at the surface, there's no pressure difference. But as you go up through the atmosphere, the pressure's falling off faster near the poles, and it falls off slower at the equator. So there's a pressure force towards the pole. Okay. So there are my pressures. And if I then draw what's the pressure gradient, well, it's higher pressure at elevation at the equator than it is at the pole. So the air wants to flow towards the pole. Are you guys with me? I can't hear you, but I believe you. And I'm thrilled that you're following. It's great news. Okay, so if we took the difference of these two hydrostatic pressure expressions and we used them to calculate change in pressure over change in the y coordinate, so with latitude, then we'd see that you get rho p minus rho e, polar density minus equatorial density times gravity times z, over some delta h, over some range, whatever we decide is the range in latitude that we're measuring over. And that's pointed in y. So rho p is higher than rho e, so that's positive. G is a positive constant. So this pressure force is pointing in y towards the pole, and it's simply varying with z. Okay. So now what can we do next? Well, oh, that's in the wrong spot. That was amazing. So now let's remember that the geostrophic velocity is 1 over whatever the mean density is, 2 rho, density is rho, omega is the rotation rate, is 1 over the rotation rate. And then it's proportional to the pressure force cross z. So it's to the right in the northern hemisphere of the pressure force. And the pressure force is pointed toward the pole, so the geostrophic response is to the right of that direction, which is in positive phi hat. So it's wrapping around prograde faster than the planet. Just like we talked about before with a low at high elevation. The pressure's low at high elevations over the pole, so the winds wrap around faster than the planet. And so if we put in that expression in that black box and put it in for minus grad p, then we get this expression. And we have y hat cross z hat. That gives us x into the page. And we can then see everything in parentheses as a constant. G is a constant. D rho dy is roughly some constant. Rho, the mean rho is a constant. Omega is a constant. Really, the only thing is it varies in z and it points in x hat, points into the page. And it varies with z. So I could take dug dz. I could take the gradient and I'd see, that would drop out the z and the gradient is a constant. So I expect a constant shear. Dug dz is a constant in this world. So it should get faster and faster as I go higher through the atmosphere, and there should be a constant gradient. That's so crazy. So that's what I should see. Ug should be near 0 at the surface where the pressure's not really varying horizontally. And as I go higher through the atmosphere, I should get stronger and stronger flow into the board, wrapping around the pole. So if I imagine that's my big polar vortex, my big bolus of blue cold air, I should have a big jet wrapping around it at the top of the troposphere at about 10 kilometers height. All right. It's called thermal wind. That's what the atmospheric dynamicists called thermal wind. They write in terms of temperature using some equation of state. We'll skip it. And it means high up in the atmosphere, there's a big eastward prograde axisymmetric flow. That's called the jet stream. And in winter, it's sometimes called the subpolar jet stream. And it's way at the top of the atmosphere, and it's just ripping around up there. Okay. So let's see if we can make one. So if I do one of these experiments and I rotate really slowly, then if I rotate slow enough, it doesn't break apart like in the storms I showed you earlier. And I'll show you a high-speed video, sped this up. We put in some red dye. And the fluid shears apart. There it is. There's that prograde shear. It's going fastest at the top of the fluid layer, which is why the dye, which was initially in a vertical line, gets tipped forward. And then at the bottom, it's lagging behind. That's this constant du g dz. That's thermal wind. That's this weird response in rotating fluids. It's actually like a spinning top. Instead of moving outwards, it tips off to the side. And you can show analogously, it's the same math for this as for a spinning top. If you go into a Lagrangian frame, you can show they're identical or they're isomorphic. Super cool. So that's what happens. You have a big bolus of air. It tries to spread out, but instead Coriolis holds it up with these swirling flows. But then that goes unstable. That rips itself apart. And when it rips itself apart, the baroclinic eddies that form, these little structures here, these little subcones, when it rips itself apart, they settle lower in the atmosphere. You're releasing potential energy. You move the cold stuff lower. So each of these eddies is lower down in the atmosphere. And you see something like this happen when it rips itself apart. And when we do experiments with our little fun tanks, you get similar structures. You really can get that if you're lucky. They got super lucky. It's not usually that clean, but for them it was. Okay, so now let's understand atmospheric rivers. We have these big instabilities. We have these big storms when the polar vortex rips itself apart, right? We have our big flow from the North Pole, and wrapping around it is an atmospheric river. Let's see if we can understand why. You might say, oh, it's just a big plow that's just pushing forward this moist air. No, the moist air is really over Hawaii. There's no reason for this storm to push it over to Vancouver. So why does it go there? We get similar storms in our tanks. We actually get similar atmospheric rivers in our tanks. We have a nice one right now, actually. What's happening is when that cold air comes down in this eddy, it's now settled down. It's only the polar cold air mass is only about 2 kilometers high now in the atmosphere. It's so much lower. When it was up at the North Pole, it was like 10 kilometers high. It was just huge, took up the whole troposphere. Now it's settled down in this big eddy, but everything else is the same. You still have cold air, dense air to the left in the blue, and now low density, I should have made that red, but low density green moist air at Hawaii. So it's the same thing. Same exact problem, but now you get this strong flow into the page off to the east happening just above the edge of the eddy. So you now have a jet, instead of at 10 kilometers, is wrapping around the eddy, right next to the eddy at about 2 kilometers height. And it steals all the moist, hot air from Hawaii and pushes it over via this thermal wind jet. It's called a low-level jet, because it's now near the bottom of the troposphere, and it pulls it all the way over to California or to Western Canada, to BC. And so the flow looks like that. You have this strong eastward jet, low-level jet at 2 kilometers, and that's where you transport almost all the water vapor across the mid-latitudes. And so what's going on? The subpolar jet forms around the polar vortex. It then becomes unstable. At its edge, you get a low-level jet, and that low-level jet carries subtropical air to the west coast of the bounding continents. When it hits the continents, you get rain. Okay, so now I showed you an experiment already. I'm now going to show you a movie, though, of another experiment that we did, really no different than what we did over there. We just filmed it carefully. So here's one of these experiments. I've transformed now into the rotating frame digitally because the camera on that day wasn't rotating. There's our big storm at about 7 o'clock, and wrapping around the storm is a beautiful red structure. Same thing on the eddy next door. There's this long filamentary line of red dye. That's equatorial, quote unquote, warm water. Warm air in this analog experiment that's being carried around by the low-level jet towards the continent on the side. So if we look again, here's the front of the big eddy, really right by that frontal zone is an atmospheric river that's caught in the low-level jet, and it happens on all of them. You can't stop it from happening. We had it happen in our experiment at the start of the talk as well. They weren't as clean, but they happened. You can't stop them from happening. So that's my story. Here's my image. That's data from NASA. And now let's put the experiment over it. And if we overlay the experiment, we get this big exploding storm from the pole, and it carries moisture from quote unquote Hawaii, and it forms a structure that's incredibly similar to what you see in the data. Why? Because the physics at 0th order is the same. In detail, there's lots of physics we're missing. This is a very simple experiment. But in terms of the fundamental processes, all you need is rotation, a lateral temperature gradient, and that's really all you need in this case, right? You just need cold at the pole, warm at the equator, and you need rotation. And you get these instabilities, and around their edges, you always get these rivers. So we just explained basically everything you see in wintertime mid-latitude climate. My apologies for not doing the equatorial climate. Humbly, I don't know much about it. I would have to get somebody else. I haven't learned equatorial climate yet in detail. And I don't yet know how to do equatorial climate on these rotating tanks. The rotational effects are much more complex near the equator. Okay, so I'm going to show you just one more thing. I don't know where I am for time. I got like 1 more minute. I'm just going to mention, if you guys like these kinds of really simple desktop fluid physics, you can go to our webpage. It's called DIYnamics. We have one webpage on YouTube. I have another one for Spin Lab, which is my lab at UCLA. And I have videos of a lot of different rotating fluid phenomenon that are relevant to atmospheres and oceans and planetary cores and stars. These are really useful tools in classrooms. We have different size tanks. You can do the same experiment on a 1 meter tank. You get the same response. You get big eddies, and you carry a lot of red stuff from equator to pole. Why? Because this scales all the way up to a planet. The physics really doesn't change. So it's scale invariant, which is really beautiful. And we can simulate other planets too. You can study the kind of eddying processes that occur elsewhere in very small tanks. As long as you get the rotation to dominate the fluid physics. So there are different tanks. We have one GitHub page. It's out of date. Don't use it. And then everything's on YouTube right now. So everything's on YouTube. And if you like this stuff, you can see, you could make your own. The whole idea of DIY is just make a rotating table somehow, and suddenly you're an atmospheric dynamicist. And you can do anything anyone else does anywhere with very simple parts. All the parts in this experiment here, this is off Amazon. This tank's off Amazon. There's a beaker. The cell phone's the most expensive piece of equipment. The motor is made by Lego. So you don't need it to be a Lego motor. It can be any motor you can come up with. If it'll rotate things, we give you directions on how to make our system. It's my friend Bill. I make videos at the same table showing how to do these experiments. And you can look them up on our page. In addition, if you do want more detail, go to the show more on these movies. And we do show more, including, how you buy the different parts on Amazon or on the Lego page if you want to go to Lego. And then we have directions for how to build everything. So if you don't want to do that, just go to our SpinLab page. We just have a million videos. So I will stop my share, and I thank you very much for your attention.
Well, thank you very much, John. It was really good, really good. Any question from you upstairs?
It's looking dark in there.
Yeah, it's looking dark, yeah.
Can we turn on any lights?
We are at the equator. These are short. Okay, so any question? Emmanuel, do you have a question?
Can you hear?
I think you can go towards the computer. It will be.
Maybe now. Thanks for the very nice talk. I enjoyed that a lot. I have a question, maybe I missed it. You stressed that you are simulating here the wintertime climate. Why only wintertime? Because the poles are there in summer too.
Right, good question. So I didn't show something important. So the size of the storms scales with the temperature difference. And so if there's a very weak temperature difference between the equator and the pole, then you don't really need to have big storms, right? So that there's not much of a polar jet. And the polar jet, when it goes unstable, it doesn't really make massive storms in summer. So in summer, you don't have big mid-latitude storms coming from the pole. In summer, you might, at the end of summer, get big hurricanes or typhoons at the end of the summer season coming off the equator. But in summer, not much is happening coming from the poles. So this still happens at the poles, but it's littler storms, and we don't care about little storms, right? Like little things you typically don't notice because they're little. It's in winter that these are just huge, and they are carrying huge atmospheric rivers that simply inundate and flood the west coast of the US and Canada at times. In the summer, that just doesn't happen because if there's not a big storm, there's not a big atmospheric river. That's another way to say it. So it's boring in the summer in terms of polar processes, but it's very interesting in terms of equatorial hurricane and tropical cyclone dynamics. Do you get it? So the interesting area switches from pole to equator when you go from winter to summer. But I haven't figured out how to make a hurricane in these tanks. And I've had a million people ask me, like, you haven't tried to make a hurricane? The answer is, of course I have. And I've simply failed about 1,000 times. But when I get to the 1,020th time and it works, I'll let Catherine know. We'll do a hurricane day.
Yes. Yes.
Does that make sense, Emmanuel?
Yes, thanks.
Great. Love it. Anybody else?
If nobody wants to ask a question, I would like to ask a question. Do we have a scaling for the almost length scale, not length scale, but width scale of these strips? Like this?
Yeah. Do we have a scaling? No. So,
No.
if we have it, I don't know it. The definition of an atmospheric river is that it's about 2,000 kilometers long and between 100 and 500 kilometers wide. But is there an actual physical scaling for relating essentially the radius of the storm, which is called the Rossby deformation radius, to the width of the atmospheric river? I think the answer is not yet. I think that's a great thing to do. I think would I do that in the lab? You could try that in the lab, but I think it'd be smarter to do it with a supercomputer. Do you get
I
it?
think so. Yeah.
Because the problem with the lab is I don't actually have any water vapor transport for real. I have red dye that I claim is moist equatorial air, analog air. I get the right physics, but I don't actually get the thermodynamics, latent heat. I don't get any of the water vapor processes. And if I were trying to come up with a scaling, I would want that in my model. So are people trying to do that? I assume, but I don't know of a clean scaling. I've never seen it. It's more, and it's a little fluffy. Atmospheric rivers are new, and the idea was only posited in the mid-90s, and so I don't think the science is that well constrained yet. And the minute you hear people start arguing about what's your definition of an atmospheric river, you know it's newish, right? It's not very mature scientifically. So people still argue about, well, what defines one? How do we characterize? Is that one an atmospheric river and is that one not? And then you hear people arguing. And the minute that kind of argument exists, it means work has to be done. It's the same thing with plumes. Sometimes with plumes, you'll hear people say, well, that's not a plume. And then you go, it's totally a plume. Okay, that's troubling, right?
Yes.
So I have a question. I'm going to ask a question then. Why did I use water to simulate the atmosphere? Oh, that's a terrible idea. So why is that kosher? Why is that okay? Anyone? Just hanging out here in LA. Anybody want to take a guess? I will say this scientifically, what's the most important thing we can do with our lives? Take guesses and constantly be wrong. And then we eventually will be right. It's just like doing 1,000 experiments to get a hurricane. If we keep failing, eventually we'll get it right. So you just got to guess. So why do you think water's okay here, when clearly the atmosphere is made of air? Anyone? All right. Okay. Maybe I'll answer it. That's fine. Better if you guys guess. Okay, so let me see. Maybe I'll share my screen for that. Sharing. Where's my talk? Okay. So let's go back there. Let's see. Where are the equations? The wonderful equations. Boom. Great. So here's our equation for the velocity. You might say it does depend on the density, but it really depends on just the local density or the mean density. And so even though the atmosphere is made of a different material, I just need a rotation rate. I can measure that. I need a pressure gradient. I can generate that with temperature, with the ice. And then I need some mean density. Okay, I have a mean density. It could either be in the air or it could be in the water, but it's a fluid in both cases. And so the fact that air is compressible and water is not is secondary in this system. It does matter a little, but it doesn't really matter that much, especially when we're talking about geostrophic flow. Everything's horizontal. On any horizontal surface, the mean density is whatever it is. So the fact that water is the same density every height, while air decompresses with height, it doesn't really matter that much for this system. Another way to say it is, well, I don't have it. Yeah. Another way to say it is, I'm going to try and find this other equation. Another way to say it is, we're taking I'm trying to find if I have this. I didn't put this equation in. Oh, well. If you look at the ratio between, for instance, any of the two terms in the Navier-Stokes equation, you also see that the density drops out. And so since the density drops out when you compare two terms, then the mean density doesn't really matter that much. It's the density differences that matter. So then I'm allowed to use any fluid I want, as long as it's a fluid and it has some small density differences. Not a very good answer. Yeah. Yeah, yeah, that was a terrible explanation. Because I don't have the right slide. My apologies. But anyways, that is, but I do want you guys to take home, you can simulate large scale atmospheric processes with quote unquote the wrong fluid, right? With water. And you can, because on these large scales, the mean density isn't a huge deal. And so the variation isn't a huge deal either. It's actually the temperature controlled differences that do all the dynamics. So the dynamics don't care that much about the fluid density, the mean fluid density. That was terribly done by me. My apologies.
Okay. And your fluid is not too viscous in water.
Right, as long as it's a low viscosity fluid. Yeah. All right, I'm going to do one other thing while we're here. I'm going to pin this. Okay, there's our experiment. Let's put in some other color. Oh, there's some green. Oh, I think I have some nice purple. Okay, there's some purple. I'm gonna put in some more red. And let's mix it. All right, I'm gonna take this big mixing mixer and I'm gonna, oh, I know what I'm gonna do. I'm gonna take out this. When I take this out, the fluid will rush in and I'll get a big vortex. So when I take this out, all the fluid has to rush in. When it rushes in, it's like a massive low pressure system, right? For a moment, I made a little vacuum right there. I took this structure out, nothing was there, the fluid rushes in. When it rushes in a rotating frame, Coriolis pushes it off to its right. Another way to say that is angular momentum's conserved. So everything starts moving faster than the rotation of the tank, and I get a huge swirling flow. Very nice. Okay, so I just made a massive vortex. That's a nice polar vortex. It was big and polar. Let's look at it for one more second, because we're patient. And then let's try to kill it. Here, wait. I'm going to get a brush. I'm gonna try and mix it out. It's okay. So now I've got a little brush to try to generate some turbulence in the tank. And let's do it. Oh, I've got this beautiful large-scale vortex. Give me one sec. And now I'm just going to do that. Oh, I totally killed it. You guys agree I totally destroyed it? It is destroyed. I trashed it. Let's give it a minute, though. When I first trashed it, the small scale turbulence that I injected mechanically really does mix a lot of the dye together. But very quickly, I return to I lose that small scale turbulence, it dissipates, and I only have large scale flows in the tank. And the large scale flows, just like in the atmosphere, are in geostrophic balance. And in geostrophic balance, I no longer have a density gradient. So du dz should go to 0. There should be no axial shears. And I make 2D vortices, big, large-scale vortices, and they really don't vary with z. You can see all the way to the bottom of the tank. And the dye doesn't mix together very well either. So I just get big, massive vortices. Now they look a little like Jupiter. And they're not varying in z because in a sense, there's no density gradients, so du dz should go to 0. And so I've really got now a fluid gyroscope. Each of these vortices is like a little local gyroscope. And it's locally trying to maintain its alignment with the background rotation. Why? Because that's the way it was initially rotating, all pointed upwards. Okay, let's do one other thing. We're just having a good time. I'm going to try and mark these. Will this work? No, that won't work. I'm going to try and ruin them one more time. And I wanted you to see how stable they are. Or they're not stable, but how coherent this physics is. So I'll try to now ruin it again. And it is ruined. There's a little 3D mixing there where I've put in all this small scale non-ageostrophic turbulence, but that quickly dies out. And I go to having huge, large scale plumes that are aligned vertically, and the dye doesn't mix very well. So we can get at all this weird planetary fluid physics that exists on large scales in Jupiter's atmosphere, Saturn's, in our atmosphere. And all we need is a little rotating tank, water, and food coloring. Kind of cool. Oh, let's do one more thing. Let's imagine our planet got hit by a meteor. And let's say it stopped rotating. Pretty quickly, all this would break apart. I'd lose all that coherence. Everything I've been talking about will just get shredded, and I'll go back to normal, quote unquote, 3D turbulence. And so as soon as I lose that, the rotation is organizing everything. If I take away the rotation, the fluid then starts spinning down and everything shreds itself. Okay. I'm going to call it a day.
Okay.
Thank you, guys. Hope that was novel.
Yeah. Any comments in the room? No.
All right. Well, enjoy your weekends and thanks for coming.
Okay, so thank you very much, John. Thank you very much. It was.
Thank you, Catherine.
Thank you.
Thanks again. See you guys.